Hello, everyone. Welcome to Rational Science. But today I'm not transmitting from Germany. I'm in South America, and I had a little bit of trouble with my internet over here. I hope everybody can hear me fine. Let me know otherwise in the comments there in the chat. Okay, so if you can hear me and see me fine, I'd really appreciate some back feedback on that. Okay. Anyways, meanwhile, I'll continue. I'm going to be covering a little bit of extinction first, and then I'm going to move on to physics. We had some issues brought up on the issue of homosexuality. Okay, so let me talk about that a little bit. Here we had a fellow, he says, there are selective pressures for the males too, and when those change, you get consequences. In the case of dimorphism, as it related to competition between the genders, keep in mind that men are no longer fighting to survive against enemies in hand-to-hand combat or predators and animals in the wild. Okay, thank you. Assuming those were pressures that contributed to the evolution of strength and power in males, when those pressures are gone, you're likely to end up with softer men that don't even have good coordination or aggressiveness. Okay, this alone might allow women to catch up. Okay, so I guess it's an arms race, and when there is no race because you don't have to fight against the element, I guess that's what he's saying, then there is no reason for women not to catch up to men. I don't know if everybody agrees with that, but I guess that's one point of view. Okay. Okay, here's another fellow. He talks about testosterone, whether you need it or not to to overcome or overpower women. Okay, says I think I read a theory at some point about less testosterone leading to less conflict. Uh-huh. I wonder how the level of testosterone in modern men compared to hundreds of thousands of years ago. Again, an issue of evolution and whether we develop more and more, or at least we used a lot of testosterone in the past because of different environment that we were in, and that we don't need that anymore today because we don't have to fight against the element. We are the kings of the mountain, so to speak, right? We have nothing to fear. Okay. Okay, another fellow says, if I can get him up here, says all human embryos start the same, kind of as women, but then eventually the gonads or something else starts making testosterone and other androgens, and this leads to major changes not only in the reproductive organs, but the whole brain wiring. Uh-huh. I suppose that the more testosterone at that stage, the more wiring gets altered. The question is whether testosterone is the deciding factor. Okay, whether if you have more estrogen or more testosterone, does that make any difference? I mean, you have again women who have primarily obviously estrogen, and you know they get in the ring, they can beat up some men out there. So I mean, I'm not sure that's got as much to do with testosterone and estrogen as it has to do with skill and strength and so on. And you will find females which are pretty strong and they have estrogen. So I don't know. The jury's still out on that one. That, I guess, was the main point that I was trying to make last time, whether estrogen and testosterone really have anything to do with strength. Remember that in the animal kingdom in general, you know, females have estrogen and males have testosterone, but again, it's the social factor, the roles that each member of the lion clan or the hyena clan have that maybe decides who has what skills, and not so much the chemical composition inside the body. Another fellow says I think it's a combination of both. And he was talking about whether it's nature or nurture. Okay? Don't know if it's more nature or nurture, though. I believe straightness is the standard simply because it's what works to keep the species going. not because sex feels good or any of those are secondary, he says, right, reasons, but it is mainly because it's simply practical. Uh-huh. All homosexual people, they like it or not, come from straight human relationships. There are physically no other ways. Well, yeah, I mean, homosexuals obviously come from heterosexual couples. I don't think you can get them from homosexual couples. And but then the question is how much nature and how much nurture there is, and if there's any nurture at all. I can only give you my 5 cents worth, and that's that I think people are born gay. I don't think they are educated to be gay. I don't think you can undo what you have inside you. And just like heterosexual people don't fall in love with their own types, I don't think in the same way that a homosexual can change his orientation. He's born with it. I think he's hardwired that way. And again, I showed last time that there's several studies. One by this fellow Schwab, and he's Dutch. And what he did, he took some brains and dead people, and he looked at the sizes of the that dimorphism. I can't remember what it was, the gland or whatever, and he found that there were differences between homosexuals and heterosexual men. Okay, so I think there is a physical difference between them, and that's something if you're going to be looking at this subject, you should do some research on that. I also read in the past a couple papers that sheep also have that issue where the males that are homosexual, they put like 10 sheep in a row and they have them there in their stalls. And here comes they bring the sheep they suspect of being homosexual. Well, they bring several sheep, but they figured out that the ones that always, they can smell all the sheep there, and they go after the males, and those are the homosexual ones. And approximately 10% of sheep are deemed to be homosexual. And when they look at the brains of these sheep, more or less like what Schwab found there, that the brains have differences. So it's something for you to ponder if you're going to be doing research on the subject. Okay, I hope I'm still alive here. I still am getting that they're not receiving enough streaming at YouTube. Can everybody hear me? Can anyone confirm that for me? Okay, because I just got a yellow sign there from YouTube. Again, I'm in South America. I'm hoping everybody can hear me still. Yeah. Okay. I don't know why I got that message from YouTube. Okay, so please bear with me. I'm worried about being, losing contact. Anyways, final issue. Here it is. Fellow says, what about human survival through mealworms? He's talking about the extinction of man. And he says, mealworms can eat just about anything, and we can eat mealworms. Uh-huh. And if you look up what is a mealworm, what's the larvae form of the mealworm beetle? What is he talking about? He's talking about maggots. That's what he's talking about, whether they're flies or... Yeah, thank you. Thank you for the confirmation. Anyways, are we going to be eating maggots? That's the first issue. The second issue is that, if you look up mealworms, they can eat apples, they can eat stuff like that, but the question is whether they can eat some weeds that nobody wants. So the diet of the worms is one issue. Then the other one is, what are you going to have? A farm, a maggot farm? Just grow maggots and eat them? Is that what it is? I don't know if that's much of a future. It might help you survive, your group or you, but it's not going to last several generations. So even if we survive, or some pockets of humans survive eating mealworms or any kind of maggot, I don't think it's got very much of a future. Okay, let's move on to Physics, we're going to be talking about mass and weight today, primarily weight. That's the issue today. What is weight? And what I'm going to be doing here is starting out with a comment that someone made, okay, related to my previous presentation, my previous lecture. It says the following. The quotes from Aristotle you present clearly are talking about densities. It takes more force to push an object through water than it does through air, and less force if the air is thinner. If these quotes, he also says that in these quotes, he also says that it takes more force to move a heavier object, which we know is also true. Gravity is different from, of course, because the force of gravity is proportional to the weight. These quotes don't mention gravity or falling at all. So this claim about iron balls falling seems to be entirely a straw man created by someone with extraordinarily poor reading comprehension. Or maybe you simply presented the wrong quotes. I don't know much about Aristotle's writings. Well, the issue is, maybe I didn't make that clear. I was not talking really about gravity. I was talking about force, and I was talking really about Aristotle's reasoning. His reasoning was that you have some resistance to flow. If you move through water, you move a little harder than if you move through air. That sort of thing. And he applied that to gravity. I didn't quote the gravity passages from his book. What I was saying, what I was referring to was what was his reasoning process. Okay, why he concluded that a heavier object falls faster than a slower one, because he carried out this type of reasoning. He was looking at what resistance that object encounters. Okay, so that was the context. I just want to clarify that if that wasn't clear the first time. Okay, let's move on here. Here I'm going to begin with a review of mathematical physics, okay, of how they look at weight specifically. Okay, and I'm going to start with force, which is what I ended up with last time. And here you have it. I was talking about force equals mass times acceleration, which is Newton's second law of motion. And I'm saying that's a push force. That's a force of push, primarily, because you're talking about where the object departs to where it ends. And what do we mean by that? Well, it's being pushed. Now you can say, well, maybe it's being pulled from the front, but they never justified that, because there is no pull from the front except like if you're pulling on a donkey with a rope. And in that case, it's still a push, because what's really pushing is the rope on the back of the donkey's neck. So it's still a push force, okay? So I'm saying that force equals mass times acceleration is a force of push exclusively. And on the other hand, the Newton's gravitational law, okay, which is that second one there, force equals gravitational constant g, mass 1 times mass 2 divided by distance squared. I'm saying that's a pull force, okay? And I don't know if they ever discovered that. They don't talk about in terms of push and pull. They just say, well, this one's the gravitational law and that one's the second law of motion. That's all they say, okay? And they apply it. Okay, what is mass according to standard, the worldly wisdom? Quantity of matter. And that's essentially how mathematical physics treats it. It says quantity of matter, that's it. Okay, that's the notion. What is weight? Summarizing, pull or push of gravity. Could be push, right? It could be push from above, but they always talk about the pull of gravity. Keep that in mind, okay? Weight then is, I guess you could say, a push under the quantum mechanics notion, because you have all these particles that are allegedly pushing the object downwards towards the earth. If you're going to do it particles, I'm not sure how you can pull by throwing particles from the center of the earth to you, right? And that's one issue. The other one is when you have general relativity, what you have is warpage of space-time. Well, somehow that what you're doing is, like in the case of a planet, Earth or the sun, it's pushing the canvas downwards. That's the notion they have. And then the whatever object, could be a photon, could be an electron, could be an atom, is rolling down that inclined plane. That's the notion they have. Okay, so it is a push no matter what. Okay, the question is, why would the photon or the electron or whatever you want to throw into that hole, why would it roll downwards? What's pulling it down there? Or is something pushing that downwards? And that's for you to figure out. But my point is that the original warpage of space is created through a push mechanism. That's the point. Okay, so what do they say? Well, they say, well, if you have the same mass, okay, you weigh differently in different parts of the universe. Like if your mass here on Earth is 100 kilograms, you would weigh only 16.5 kilograms on the moon. Okay? And they really have no explanation for that. What they use is mathematical description. They say, it is so. You weigh here 100 kilograms, you go to the moon, you weigh a little less, right? And you can prove it with astronauts going out there. Great. What have we learned? We have a description, but we don't have a mechanism. Are they being pulled towards the center of the Earth? Are they being pulled to the center of the moon? Or are they being pushed by, I don't know, particles coming from outer space? What's the mechanism? Okay? And we do have a mechanism under the rope model. And here it is. Okay? Okay, here you have it. If you have a bigger object, such as in this case, the Earth, okay? As you can see, it's a little bigger than the moon, okay? And so there's a lot more ropes connecting every atom on Earth to one atom of the astronaut. It's tied to that foot of his, in this case, in this example. And there are a lot fewer atoms on the moon, and they're pulling on that same atom, but since there are fewer atoms, you have fewer ropes. In fact, fewer independent ropes. That's what we call them, because they have to be pulling in, or really it's a tension, but we'll use the word pull for the sake of argument. What I'm saying is that you have fewer ropes acting, okay, in the case of the moon, because there are fewer atoms on the moon that comprise the moon than the Earth. Very simple, straightforward kindergarten stuff, okay? You don't need to know any more than that. So we have a solution for why that's the case, why you're being pulled more towards the center of the Earth than you are being pulled towards the center of the moon. Okay, so you might say, well, what's pulling? I mean, how do you know there are ropes that are pulling on each atom of your body? Okay, so now we introduce a little evidence, okay? People like evidence, they want proof. Okay, so let's introduce some of that. We don't go for proof and evidence in rational science, but a lot of people say, prove it to me, Bill. Okay, let's prove it. Let's move in there. Let's go with that. Here's Mr. Richard Muller. He's a professor at Berkeley. I think he still is. I don't think he retired yet. And he says, for example, if you have the Earth, there's a big mass here, referring to the Earth, right? And you have you with your little mass here. That's you there, a little drawing of a human on top of the Earth, the big mass and the little mass, okay? Every atom on the Earth is pulling on every atom of you. Let me repeat that. Every atom on the Earth is pulling on every atom of you. Richard Muller, not me, okay? That's what he says. You're also pulling on it. Okay? The amazing thing about gravity is that it goes right through things. Okay? So, how do you pull on every atom on Earth, and how do you get gravity to go right through things, right through walls? You have an astronaut, he's in outer space, and he wants to create this gravity shield. He wants to protect himself from gravity so gravity doesn't touch him. So he puts a shield in front of him, and it turns out that the Earth attracts the shield and attracts him right through the shield. Both of them. And the moon and whatever's behind him. How do you do that? Unless every atom in your body is connected to every atom on Earth. That's what Mr. Muller is saying. Okay? That's the theory. So we have a way of showing that, and essentially, that Newton's gravitational law is sound. It's consistent with the rope model. No problem there. Okay. Now, how about the establishment? Well, for that, we have to go to the word weight. What do we mean by weight? Okay, let's find out. This is the official version, by the way. Okay, here we go. Weight, you look it up. This is from the Wikipedia. Weight, the force acting on the object due to gravity. Okay, and then you have the simple equation, weight equal mass times gravity. In this case, the gravity on Earth, which is 9.8 meters per second squared. Okay, that's the acceleration of gravity. Okay, represented by the letter G, little letter G. Okay, but then we find out that there are a little bit of some problems here, okay? And it's got to do with the definition. That's the official definition. Now we go to all the fine print, okay? Some standard textbooks define weight as a vector quantity, the gravitational force acting on the object. Others define weight as a scalar quantity, the magnitude of the gravitational force. Yet others define it as the magnitude of the reaction force exerted on a body by mechanisms that counteract the effects of gravity. Now, how's that? We have at least three notions, three definitions, three descriptions of what weight is. And just in case, it says further complications in elucidating the various concepts of weight have to do with the theory of relativity, according to which gravity is modeled as a consequence of the curvature of space-time. Guess who came up with that one? The current situation is that a multiple set of concepts coexist. So we start off on the wrong foot because we already have all these, at least four definitions. There are four notions of what weight is. And the mathematicians don't care. They use this stuff. They don't care about the qualitative stuff. So they could care less. They can live with this stuff. Okay? Anyways, you see it says weight equal mass times the acceleration of gravity, that little g there. Where did they get this? Let's find out. Okay, here we have it. Give me a second here. Okay. They get it from force equals mass times acceleration. Newton's second law, okay, of motion, which is a push mechanism. And if you turn that around, you play around with that, you get mass equals force divided by acceleration. Okay. Now this isn't a math course. Here I'm trying to just get the notion, the qualitative notions out of this, okay? We're not going to be doing numbers or anything like that here. Okay, so you can see acceleration is a dynamic concept. All three of them, all three variables there are dynamic concept. Velocity is a dynamic concept, time is a dynamic concept, and so is acceleration. So they're talking about motion here, okay? And yeah, force had better have motion because force, above all, is directional. Whether you push or pull, the donkey has to move 1 inch at least in one direction or the other. Okay, keep that in mind. Force means you got to move. You can't stay in your same location. That's my point. Okay, so we look at, what is that velocity? Well, velocity includes speed. What is speed? We move a little higher there and it says speed is equal to distance divided by time. But what's the problem there? That distance is not distance. Not in mathematics. In physics, yeah, distance is distance, separation. Here we're talking about distance traveled. Again, it's a dynamic concept, so they're talking about displacement of some kind, some motion. But if you want to have velocity, that's not enough to have speed, which is just distance traveled divided by time. You need one key issue, which is direction. You can't do velocity without direction. And that's quite in line with the word force, because force is motion in a given direction. So we're okay there, okay? Where's the problem? Well, the problem is weight is location specific. Weight carries no motion. Okay, let me repeat that. You have a given weight only for a given location somewhere in the universe. You change your location, your weight changed. So weight is location specific. There is no motion. But here they're talking about using Newton's second law of motion, which is what? A law of motion, meaning he's going to move from location to the other. So the question is whether they can use this equation, force equals mass times acceleration, to calculate weight. Is this the equation of weight? Well, you saw that weight included the gravity on Earth, the little g, acceleration of gravity. That's that acceleration there. But you need the Earth. You need a second object. So we're not talking about one object moving towards the Earth. We're talking about two objects, and we're talking about location. We're not talking about acceleration or motion or anything like that, or distance traveled. You're talking about separation. So you can't use this equation. This equation is the wrong equation to use for weight. You can't use it because this is dynamic equation for force. Okay? And here you see it. Okay, this is perhaps the equation we should be using. We should be using Newton's gravitational equation. Okay, so we should replace that force equals mass times acceleration for weight equals mass times the acceleration of gravity with force equal, at least as a starting point, right? Force equals the gravitational constant g, mass 1, mass 2 divided by distance squared. Now that is a gravitational equation, and that's what weight is. Wasn't it defined as a gravitational phenomenon? Okay? And I'm going to argue further that this is not even an equation of force. It's an equation of tension. Tension is not a force. Force is not a tension. There's only two forms of contact we call force, and that's push and pull. Tension, no one wins the tug of war. Okay, let me illustrate that here. Okay, no one wins the tug of war during tension. And the problem is that, what they've done over the years is define tension as a pull force. That's what everybody thinks it is. So they always put it under the word pull. They think it's a force of pull of some kind because one guy's pulling against the other. That's the way they look at it. It's not, because tension is like if you hold a stick made of a single piece, because you're frozen in time. There is no motion. You have a single frame in the universal movie, and that's what tension is, that's what weight is, and that's what Newton's equation is. Because, that changes according to distance. What distance? Is it the distance traveled? No, it's the separation between two objects. What two objects? Mass 1, mass 2. That's what the equation tells you qualitatively. Okay? And here you see the difference between force and tension. Okay? These are the definitions. You see force and influence, that one can do what? Change the motion of an object. If you change the motion, what you've done is change locations, because motion is two or more locations of an object. So when you have motion, you change location. Once you change location, you do have force. Okay, force can also be described, I like the word that they use, describe, intuitively as a push or pull. Push means you change locations. Pull means you change location. Whichever one you use, doesn't matter, you change location. A force has both magnitude and what? Direction. Okay? Weight does not have direction. It really doesn't. It is a tension between two objects. There is no motion. You don't know in which direction it's going to move. It's just a static situation. That's a static predicament. Okay? Tension is what? Well, this is their definition, okay, by the way. The pulling force transmitted axially along an axis, right, by the means of a string, a cable, chain, or similar object. Okay? So all I'm saying is they use the word pull because they're thinking that tension is the stretching. You're stretching. You're stretching the rubber band, so to speak. And it wouldn't matter if you stretch a string or a rope or whatever, but think of it as something that's being stretched. That's what they think of it. So they think it's changing locations gazillions of seconds by gazillions of seconds. So they think they're stretching something. No, that's not tension. What tension is a tight game. Nobody wins the tug of war. Okay, so it's a tied game. No, there is no motion under tension. Tension is a static concept. Okay, so let's move on here. This is the definition of the word mass now. Keep that in mind, okay? We're going to compare mass against weight. We already looked at weight. We're saying weight has no motion whatsoever. What is mass in comparison? Well, you start out by saying in mathematical physics, one may distinguish conceptually between at least 7 different aspects of mass. 7 different notions that they have of mass. There are a number of ways that mass can be what? Measured or operationally defined. What is an operational or functional definition? It's an irrational definition because it's an after-the-fact definition. You do an experiment, you do an observation, and that is what retroactively was your definition with which you started out your presentation. That's what an operational definition is. And they're talking about measurement. We're not talking about measurement. We don't care how you measure mass. We want to know what mass is. What is the definition of mass? And here you have a couple examples, 6 of them. Inertial mass, active gravitational mass. What is that? A measure of the strength of an object's gravitational flux. Passive gravitational mass is a measure of the strength of an object's interaction with a what? Gravitational field. Sounds like weight, doesn't it? Energy also has mass according to the principle of mass-energy equivalence. Mr. Einstein there, E equals mc squared. Curvature of spacetime is a relativistic manifestation of the existence of mass. And finally, quantum mass manifests itself as a difference between an object's quantum frequency and its wave number. So which one of these should we use? I mean, here we have 6 notions of mass. They're telling you there's 7 notions of mass. I can tell you 2 off the top of my head. One is relativistic mass, which they use in special relativity, and that goes against what? Inertial mass. So you have inertial mass on the one hand, you have relativistic mass on the other. And what is relativistic mass? Well, it means that if you move faster and faster, almost at the speed of light, you gain mass. And if mass is the quantity of matter, I guess you're gaining atoms as you go faster and faster. Is that what it is? Or are you pressing stronger and stronger, harder and harder against the scale? Sounds like weight. So is there a difference between weight and mass? It looks like there ain't, because, here you have this relativistic mass, and all you're doing is pushing against something which they say, well, your mass increases. Surely you're not increasing the quantity of matter in your body. What you're doing is pressing down harder because of your speed against the scale. That's what you're doing. So yeah, it looks like they're confusing mass with weight. Okay, and yeah, there is no difference unless someone can show me that if you take something to the moon, right? And they say, well, the mass stays the same. What changed was the weight. Well, how do you know that if the way you determine mass is not by counting atoms, which would be quantity of matter? No, the way you do it, you put it on a scale of some kind and you weigh it. And you end up with so many kilograms. And how do you measure your weight? Don't you measure it in kilograms also? So I don't know what the difference is. Maybe someone can tell me. Someone can clarify that in very precise ways, not a one-liner, because certainly you won't do it with that, okay? And here we look at the differences here. It says mass is both a property of a physical body. What are they referring to? It looks like they're referring to the quantity of matter, right? And a measure of its resistance to acceleration, which sounds a lot like weight when you look at the acceleration of gravity. Okay, so again, we don't see any difference there. And if it's quantity of matter, what do? We count little atoms of how much the table is made, a gazillion atoms. Is that how we do it? Or do we weigh it? Okay. Mass measured in what? Kilograms refers to an intrinsic property of an object. I thought we weighed our weights also in kilograms. I mean, when they ask me, I don't tell them in what it says next. Their weight measured in what? Newtons? Measures an object's resistance? Well, I don't know. I don't give my weight in newtons. I never have. I always give it in kilograms, which is what? Mass. And if you weigh the mass, then all you're doing is you're not telling me how much matter it has. You're insinuating that, but you're not. You haven't counted atoms. I mean, if mass is the quantity of matters, you would say, well, Bill weighs 1 gazillion atoms. Then, or has a mass of 1 gazillion atoms. Then we would understand it, because that would be quantity of matter. But if you say 1 kilogram or 10 kilograms, 100 kilograms, now you're not talking about anymore about counting atoms, quantity of matter. Now you're giving your value in a measurement instead of in counting. Counting and measuring are two different things. Counting, you count apples. Measure, you measure a table. Those are not identical ways of determining something. Okay, so again, they determine mass through weight, and then they say, but they're different. Why are they different? Because on the moon you weigh differently. Well, how do you know if or your weight is different, but your mass is the same? Well, how do you know the mass is the same if you're going to determine mass through weight? By weighing, by putting it on a scale. So this is the issue. It's a circular argument, because they have never been able, since the days of Newton, to determine the difference between mass and weight. They define it differently, they give you the runaround, but they cannot put their finger on it. They can't show you what the difference is. And the reason, again, is that they don't count quantity of matter, ever. They never have, and they never will, because nobody's going to take the trouble counting every atom in the Le Grand Kilo, for example, okay, which is the original standard that we had for the kilogram. Okay, I just want to confirm that, yes, mass is the quantity of matter. Here is evidence, proof, what people want out there. Okay, here you have it. Mass is a measure of the amount of matter in a substance or an object. Flexbooks. Mass as quantity of matter. The paper in Publication Med. Confused? You bet. Mass is the quantity of matter in a body, regardless of its volume or of any forces acting on it. The term should not be confused with what? With weight, which is the measure of the force of gravity acting on a body. How it works daily. Wherever you go, I mean, you don't have to take these. You go, just Google it and find out what mass is, and you'll find out that a lot of people, just most of the people out there, think of it as the quantity of matter. What is quantity of matter? You count apples. That's what quantity of matter is. You got 100 apples, that's quantity. If you're going to measure how much they weigh, 100 apples weigh, now you're giving me the weight. And they say, well, it's the mass. So what is weight? Well, mass and weight are the same because, well, we're measuring it against the gravitation of the Earth. They weigh different on the moon? Yeah, they weigh different on the moon. Did you count how many apples you had? I mean, yeah, you can say, well, those same apples, I still have 100 apples, but they weigh different on the moon. Yeah, we do that with apples. Now do that with, I don't know, Le Grand Kilo, do it with a human body, do it with an astronaut. Then we'll know that you're on the right track. Okay, here's the summary, the conclusions. No definitions of mass or weight. In fact, what did I show? 4 definitions of weight, 7 definitions of mass. So what we take our pick, we get to pick which one we want. Is that what it is? So other than that, mass is equal to weight because they have never been able to isolate mass from weight. By the way, I think it was Newton who created, or the first guy who separated mass from weight in his Principia. I don't know if there was a previous precedent, okay? But he's the guy who, I think, separated them. But again, it's just a mathematical trickery, just a maneuver. Yeah, you go in there and you say mass is this, weight is that, and this is how we determine this and how we determine that. That's all it is, just a bunch of definitions. But they can't make them count because, again, we don't count mass. We don't count the number of apples. Tension is not a force. Why? Because it doesn't meet the definition of the word force. Force is motion. Tension is no motion. Think of it as a rod made of a single piece separating 2 objects. You take a snapshot of that, that's tension. Tension means no one wins the tug of war. You have a single frame of the universal movie, cross-section of time, if you will. And what you have is, think of it as a single piece. Okay, so you have 2 objects like a dumbbell. Okay, and dumbbell made of a single piece. That's it. That's tension. Tension, there is no motion in either way, supposedly because they're under tension. You know, in tension, they think, well, they're pulling. Okay, so if you pull something that can stretch no longer, now it's under complete tension, the most tension that you can think of. Now what's moving? Now nothing's moving. Now the rubber band is stretched to the maximum limit. And so now you have tension, complete tension, 100% tension. There is no motion within that rubber band. So tension, you have to think of it as a single piece rod that separates two objects. Newton's gravitational equation, force equals gravitational constant, mass 1, mass 2 divided by distance squared, is about tension and not about force. That's a tension equation. Okay, because weight is location specific at a given distance from, in this case, the Earth. The astronaut is, 100 miles from the Earth. You take a snapshot of that. That's his weight at that location. He moves a millimeter, he has a different weight. Period. We're done. Because that's what the equation says. Not because that's what Bill says. That's the equation tells you that. Newton's gravitational equation, what is it? Pull. Why? Because it's the separation between two objects. It's mass 1 versus mass 2 divided by what? Separation. That distance there is the qualitative separation between two objects. And Newton's second law, which is the force equals mass times acceleration, that's a force of push. Why? Because you're going to have motion. Not only do you have motion, but you have something else. You have direction. It's moving in a given direction. Force, in Newton's second law, is a vector. It got magnitude and direction. That's not the case with the gravitational law. Okay? Okay. We had some questions from last week. Last time I saw you, I was on a trip. And I'm not getting high or anything like that. I mean, I was on vacation trying to move around. Okay, here's the first one. Fellow says pseudoscience. He brings this subject of pseudoscience. Good subject to discuss. Yeah, there are pseudoscience. There are irrational theories out there. That's what we called it. And here's some examples. Irrational theories. Particle at two places at once. How's that for an irrational theory? Big Bang, creationism. Something comes out of nothing. Don't tell me about it. Just explain it to me. Give me the mechanism. How does something come out of nothing? Even in this case, even without God. We got rid of God in Big Bang, remember. God doesn't exist there. It's just, Big Bang is just the explosion of matter and space, by the way, and space, very important, and space, from nothing? I don't know, because space is nothing, but you figure it out. Black hole, zero-dimensional singularity that pulls on stars that are gazillions of miles away. And what's the mechanism? Again, irrational theories. And dark matter, what is it? The galactic problem, rotational problem. What is it that they had to sprinkle all this dark matter on the outside of a galaxy to maintain the integrity of the galaxy? Yeah, I mean, I could sprinkle little stars there as well, you know. I'd bring the fairy godmother and she, moves her wand around, creates this magic, sprinkles dark matter around the galaxy. All these are irrational theories. And then they have irrational terms. Why? Because none of these are defined, first of all, but then even worse, they use these concepts and they reify them, turn them into objects. Energy. And they turn it into mass, which is actually another concept. But it's like they're saying this fog that's out here, this cloud, this mist, suddenly turns into a rock. That's the notion they want to give you. But both energy and mass are concepts. Okay? And energy has not been defined. And Mr. Richard Feynman's Nobel Prize of 1965, he said it very clearly. We have no idea what energy is. Now, how's that for a definition? Field, what's a field? Well, field is out there where you play football, right? That's called a field. I don't know of any other field that's physical. Other than that, you have a gravitational field, an electrical field, a magnetic field, okay? And those are concepts. What is a field? Field is defined as a bunch of numbers that around ground zero. That's it. That's what it is. Bunch of numbers that get weaker as you get away from ground zero. And that's a concept. And so when the problem is they turn that word into a physical object, they start using it as an object. In the case of waves there, which the field is associated with the transverse wave, you know, Maxwell's transverse wave, what you have is vectors. What is a vector? Magnitude and direction. They put a little Indian arrow in there, but that Indian arrow represents magnitude and direction. And those are concepts, and you have all these arrows, they're moving sideways. Very, very scary stuff. You know, I mean, you have all this magnitude, all these 5s and 6s, they're moving. You know, sometimes when I'm drunk it happens, you know, perhaps. And that's what a wave is. What is the wave? What's waving? We don't know. It's just a wave of vectors. Particle, I put it in there because the particle, I'm referring to the quantum particle. What is that? It's a zero-dimensional point particle, so-called point particle. And what is that? That's a nothing. What it is, a collapse of the wave function. That's what it is. So when you look at the word particle, you have to think of this mathematical thing, this function that collapses. Is that a physical object? And that's how they use it. Vortex, what is it? Tornado of what? What's vortexing? What's moving around? What's tornadoing? That's what you got to identify. Tornado, we all know what it is. I mean, it's a bunch of air that's moving in circles. No problem there because air is made out of atoms. But here, what's this vortex? Ether, bunch of particles that are waving up and down, I guess, to create light. Ether is just a bunch of particles. That's a concept. A bunch of particles is not a physical object. Okay? An object is that what you can point to in a static image. That's not what ether is. So yeah, that's the first problem. Then here you have the second problem, okay? Pseudoscience, the definitions. Any of various methods, theories or systems as astrology, mathematical physics, or clairvoyance considered as having no scientific basis. And I guess we're going to include all of mathematical physics in there. Pseudoscience consists of what statements, beliefs, or practices that claim to be both scientific and factual, but are incompatible with the scientific method. Absolutely. Mathematical physics, none of it is compatible with scientific method because the explanations they give you, the theories, are all irrational. So, you know, all of mathematical physics falls under pseudoscience. Not a single piece of it survives. And here it says pseudoscience is often characterized by contradictory, exaggerated, or unfalsifiable claims. I got a problem with unfalsifiable because that's Popper's criterion, Karl Popper, Austrian philosopher. And the problem I've got there is that unfalsifiable is by whom? By the Pope? Dalai Lama? Who falsifies it? I mean, you might think it was falsified to you. What's true to you is false to me and vice versa. So falsifiable is not a very good criterion to determine what science is. And it continues, says, reliance on confirmation bias. Again, that's confirmation means opinion, rather than rigorous attempts at refutation. Again, opinion. This is not about refutation. It's about understanding a theory. Lack of openness to evaluation by other experts. Experts? I didn't know there were authorities in science. Who's the expert? Plato? Maybe Galileo? Newton? Are they the experts? Absence of systematic practices when developing hypotheses. Okay? And continued adherence long after the pseudoscientific hypotheses have been experimentally discredited. Sounds like mathematical physics. I mean, these people continue with warp space, particles at two places at once, even after all that has been discredited. You can't even imagine it. So how can it be credited? How can it be proven or non-refuted? Okay. The term pseudoscience is often considered pejorative, particularly by purveyors of it, because it suggests something is being presented in science inaccurately or even deceptively. Man, that's a full description of mathematical physics right there. Okay, here we have the issue of cult. I think the same fellow brought up the word, a particular system of religious worship. Ah, that certainly sounds like general relativity, certainly sounds like quantum mechanics, especially with reference to its rites and ceremonies. Well, there you have the examples. We have space-time for general relativity, point particle for quantum mechanics. Rites and ceremonies, you get the Nobel Prize, the Templeton Prize, the Wolf Prize. What is all that? Those are ceremonies. Those are beauty contests. You get a little crown on your head, you walk with your bouquet of roses down the catwalk. Is that what it's all about? An instance of great veneration of a person, ideal, or thing, especially as manifested by a body of admirers. Okay, I guess they're talking about Plato, Isaac Newton, Albert Einstein, Nikola Tesla. Is that who they're referring to? I mean, a lot of people worship these names. You talk about Einstein, I mean, you can't even touch the name of Einstein. That's what these people talk about. They worship him. So I guess, all that falls under cult. And finally, a group having a sacred ideology and a set of rites centering around their sacred symbols. Well, you have black hole. Everybody worships the black hole, the standard model, all the particles. None of them, you never see a single picture of a single particle, but it's already taken for granted. It's the cross, right? The one you pray to of quantum mechanics, of mathematical physics. You have some people who believe in sacred geometry. Sacred? What the hell is that? Now that's cult. That's what is known as a cult, yeah. So, just be aware that there are people who try to bamboozle you with some of these pseudosciences, and they form cults. And the cults have become religions now, because you have these they were cults a long time ago. Now they've become religions. They've incorporated a lot of these things, and now it's just part of the catechism. It's part of their indoctrination. So you go to colleges, and this is what they give you. They just read you the party line. That's what you're supposed to memorize if you want a degree. And if you buck the trend, you're going to be in a lot of trouble, because you don't get your degree. You won't even get an advisor. Okay? Okay, another fellow says, if strings produce the tensile pull force, also known as gravity, have you explained how they produce the push force that keeps objects apart? He's talking about the rope, okay? Here's the rope. Okay? So he's saying, how do you produce, I guess, push with a rope? Well, we have to start at the beginning, because here he's got several errors, okay? So let's go with the errors first, okay? The first one is strings. What the hell is he talking about? Maybe string theory? We're talking about ropes here, and we defined the rope quite well. We described, we showed the rope. It's a two-strand coiled rope, pair of strands, and they're not strings. That's the first one. So this fellow hasn't done much of a research on the case if he's going to use the word strings. I don't know what he's referring to. Then he talks about tensile pull force. Well, I just covered that. Tension is not a force. Okay? And certainly it's not a pull. Okay? Tension means nobody wins the tug of war. Okay? So tension is not a force, so correct him there. And only two forces, push and pull. That's all the ones we know of. And tension is not a pull. And then no such force as tension, okay? And this is the context. The context is that you can't pull with particles. Can you imagine pulling with those particles there? I mean, here you have a cross-section of time. God has essentially stopped everything from moving. How do you get that to move? Do you get one atom to move at a time? Is that what you do? One particle to move at a time? And with pull, you have this situation. Let's connect all those little dots, okay, all those little particles. We're going to assume they're atoms, and here we connected them. Okay, so they're all connected now. Now you can imagine not only, first you can imagine pull, you can imagine action at a distance. But it turns out that, you know, when one of those atoms moves and hits another atom, well, then you're going to have your push force. You're going to have atom against atom, surface against surface. So there is no problem under the rope model for that. And let me just say the following. You can also push with a rope, not that it is part of this context here, okay? But here it is. Let me show you this. Here you have a rope. And you can do this at home, always in the presence of a trained relativist, okay? So you torque the rope, and here at the end, you're going to feel a push, a little thump against whatever's connected to this end. So you can torque the rope. Whenever you torque, there's always this motion in which you feel a thump there. And so the rope does produce a push of some kind. Remember, we're talking about something very, very tiny, very, very thin that connects two atoms. You can't even see or touch that thing. But you can do it with a torsion. When you torque something, it does create that some kind of motion there that you can easily identify as push. But the point here is that first with the rope, you can produce action at a distance, and when the objects come together, they push each other away or merge sometimes. So we have no problem with push. It's the particle that has problems with pull. That's where the problem is. Okay, another issue. Fellow says, René is right, referring to René Descartes. Okay, there is no such thing called empty space. This fellow saying that, okay? There can be no space without substance. Descartes would probably agree with him, there is no such thing as empty space. But when he included that second portion, that second statement there can be no space without substance, now we run into trouble. Okay, that's not what Descartes said, but this is what this fellow understood. Now there you have space with substance and space without substance. Okay, so there you have the comparison. So there is a space without substance. What is that? That black stuff, that nothingness? There's no object there. There's no particle there. There's no rope there. There's nothing there. Could be between two galaxies, a region that has no matter whatsoever, no ropes crossing specifically in a given portion of space. But more important than that, you need to have space to give a backdrop, a background to whatever object you have, even to the rope, even to the particles of quantum mechanics. How do you understand particles without some contrast? And here, let me show you what I'm talking about. Here's good old God. Okay, first let's go with him. And here's God in space and God without space. I mean, if you remove all space, I guess God is infinite, is a single block of what? In this case, a black block. You need to provide contour or backdrop to God in order to see God. Okay? And so here you have my analysis. Space is not a thing. That's the first one we have to talk about. And exist only refers to that which are things. You can't have a non-thing existing. Okay? So you can't talk about the existence of space, the existence of nothing. No such monster. Okay? Thing, that which has shape, space, nothing, right? Synonym of nothing, that which doesn't, okay? Nothing does not need something. That's the one I want to clarify to this fellow, okay? Nothing does not exist with or without something, okay? It's the somethings that can exist, not the nothings. And then God needs space, okay? He needs a little bit of space. Give him a little room, okay? God is nothing without nothing, okay? If you remove nothing, God is nothing. He's a single block of whatever, because it's the space that gives him contour, okay? And let me give you another example here. This is the ether, the famous ether. What is ether? A bunch of particles. That's what it is. Okay, what happens if we remove the black stuff? What happens if we remove the space, the nothingness? Well, this is what you would get. How's that for removing space. Yeah, it's space that provides the contour to each particle. Otherwise, you would have a single block of white, a block, an infinite one. You would have, I guess, nothing. I don't know what that is. So this is the issue. These people want to give you the notion that you cannot have space without something in it, and that's not true. Space is something different than the something. The nothing is different than the something. You can't confuse those two and say, well, one can't live without the other. Well, the objects cannot live without space, that's for sure. Now, can space live without objects? I would say, yeah, space can live without objects. I think there has to be space out there that is not crisscrossed by ropes, that is not occupied by objects, by particles. And it's very simple to figure that out. There can't be that because every particle has to be contoured. You have to have a backdrop to conceptualize the word particle, or the thing we call particle. You can't have a particle without something contouring it. What are you going to contour it with? Another particle? Well, what separates the two particles? What is that dividing line if not space? What's contouring each particle? That's the question you have to answer. Okay, final issue I think here. Some fellow says, all causal influence is transmitted by direct contact between material entities. Correct. I agree there. Are you talking about 1D strings? Oh my God. No, 1D strings belongs to string theory. We have 1D nothing. There is no such thing as 1D object. A 1D object is one that the mathematicians invented. And they're not even referring to object. When they talk about 1D, one-dimensional, they're talking about an itinerary that is a straight line. That's what they're talking about. Or maybe it could be a, what do you call it? Geodesic, which is a curved straight line, if you want to think of it that way. It curves through the fourth dimension, I guess. Or in our dimension, our three-dimensional world, it's a curve, and in the fourth dimension, it's a straight line, which means it's not either a straight line or anything like that. It's an itinerary that is curved around the Earth or around a sphere, and they say in the fourth dimension, it's a straight line or a straight itinerary. You figure it out, a displacement. Anyways, from the so-called the string theory. Yeah, again, this fellow is confusing string theory. And what you're seeing there, those little strings they say, well, those are one-dimensional strings. Again, no such monster, because every one of those little lines that you see there is at least two-dimensional. That's the first issue. The second one is that they say that that thing there somehow vibrates as it's expanding and contracting there. And what it does is what you're staring at are supposedly particles of quantum mechanics. Primarily what? The graviton, because that's the one that string theory is concerned with. So what you're staring at there are not strings. The word string is very misleading, okay? Because you're thinking of some physical object, and there are no such thing as physical objects in mathematical physics. Physics with quotations again. There are no such things as things. What they have are equations. They're not interested in explanations or mechanisms, which require objects, obviously, for physical interpretations. They're talking about descriptions, and they're talking about the motion of objects and how you describe them mathematically. That's what mathematical physics is into. So you hear the word string and you say, oh, they're talking about some kind of very tiny, very thin string. No, they're not. They're talking about an itinerary of a particle. That's what they analyze at the universities or all these think tanks that are out there. What they're doing is analyzing motion, fellas. Okay? There are no such thing as strings in string theory. And with that, I'll see you on Sunday if everything goes well. And I hope I got through to everybody.